This is it. Are you ready? Reminder, if you're just listening to this, you just started seniors. This is not a unit you are required to do. You are exempt. All the details are in the written thing. But if you really want to know, if you want to see the atmosphere, if you want to know about all the good stuff, here we go. All right. Weather, atmosphere, air, earth, wind, fire. Here we go. Just nice little pictures, some weather moving in. Nothing funky, nothing crazy. Okay. Weather is the state of the atmosphere at a given time and place. That's it. That's a good definition for weather. It doesn't have to do, don't think of precipitation, don't think of temperature. It's the state of the atmosphere. So it's the state of the air around at a specific spot at a specific time. Climate is long term. Take that same spot or region and look at the weather for years and years and years and years and years and years and years, 30 years or more. All right. There's not really a specific number, but I know when I was a kid, I was told weather is this week, climate's at least 30 years. There's nothing you're not worried about in between. Right. So, big trends, climate. Cold one day, hot the next day, weather. All right. What do we have in our air? What is the atmosphere? When you breathe in, breathe out, what do you get? Here you go. 78% of the air around you is nitrogen. In fact, this nitrogen is dying into 21% oxygen. This one goes ahead and throws argon with the other gases in there. Argon is actually the next biggest thing. Then carbon dioxide, then other. I don't really like how this graph combined argon with the others. All right. Nitrogen, that's two nitrogens. Nitrogen oxides, okay? So there's nitrogen monoxide, nitrogen dioxide. Nitrogen and oxygen stick together. Oxygen sticks by itself. Ozone is three oxygens. Argon just does its thing. Water vapor, carbon dioxide, carbon monoxide, methane, sulfur oxides, whether it's dioxide or trioxide. Those are different things. All of those are in the air we breathe. A lot of the nitrogen, not a lot of anything else. All right? But 78%, 21%, less than 1%. All right? Because that's 99 for those two. So let's see what we got here. Other things that are in the air. Water vapor. It was listed on that last page. Let's see if I can do this. Yeah, I can. I know my keyboard shortcuts if it loads. Water vapor. Right here. Some places it's 0 to 4% of the atmosphere. But remember that includes clouds, that includes rain, that includes humidity. Water vapor goes 0 to 4%, and it varies a lot by place, by location. Ozone. Ozone is another one that varies a lot by location. That's what this one is. Ozone also varies by season. A lot of ozone at the North Pole, none at the South Pole, none at the South Pole 6 months later, right? So, spring, summer, fall, winter. If you read the bottom, fall, winter, spring, summer, that's the southern hemisphere. So, how about this? March, June, September, December. Going clockwise like that. You see that the amount of ozone changes. There's less. Ozone, good or bad, ugly, neither, none of the above. What is it? Ozone is just three oxygens. You're like, well, okay. No, you can't breathe ozone. your lungs don't break down ozone. If you breathe it in, you better breathe it back out, or you're going to get in trouble, right? Ozone is not oxygen your body can use, even though it's just three oxygens stuck together. Ozone is made way up in the stratosphere. We'll talk about where the stratosphere is later. Ozone is made up in the stratosphere, and it takes that altitude because there's UV light coming from the sun. And the UV light hits oxygen and spreads it out. Now you've got two single oxygens running around, and they find an oxygen that's stuck together, and then bam, collide. So you need UV light to break apart some of the oxygens, and then you need a lot of oxygen still running around. That's how you get ozone. There's catalysts. You can do all sorts of other things on there, but that's ozone. Again, the hole in the ozone, very little of it. Ozone is good for Earth because it blocks UV radiation. If there was no ozone layer, we would all have we'd have worse sunburns, skin cancer would be higher, lots of other plants and animals would have trouble too, not just humans. So an ozone layer blocks a lot of solar radiation, UV solar radiation. So that's a good thing that it does. Ozone in the atmosphere, I was going to show you. I kept this page up, not because we need another picture for ozone, but because a reminder. Sorry. Nitrogen, 78%, oxygen, 21%, argon, just less than 1%, carbon dioxide, 0.04, and then all the other stuff is 0.0000, like is very, very little. Water varies. All right, here's what I was going to show, that ozone, very little of it on the ground. Right here in the stratosphere, it peaks and then it decreases how much ozone there is by altitude. That's why I kept this page up. That's all. And you can look at it different ways. Holes and different things. All right. So, get rid of that. There we go. So ozone is something else that's in the atmosphere besides nitrogen, oxygen, argon, carbon dioxide. Besides the main gases, that's ozone. You can have something else. There are bad things in the atmosphere. Pollution, not good. Okay. Air pollutants. There are primary and secondary pollutants. What in the world does that mean? Primary are things that are emitted, things that actually are put out. Secondary are the chemical reactions that happen in the atmosphere that make other pollutants. So, carbon particulates, carbon monoxide, nitrogen oxide, sulfur dioxide, sulfur, right? Those are exhaust and all the bad things we pollute with. Then secondary air pollutants, okay? Organic aerosols, right? Hold on, where we go? Here's my chart. So carbon monoxide, things inject direct pollutants. Carbon monoxide, nitrogen oxide, whether it's nitrogen dioxide or trioxide or sulfur, same thing, sulfur dioxide, VOC, volatile organic compound. You'll see a lot of paint now is sold as low VOC, and that it doesn't have this pollutant in it anymore. Smells different, doesn't have that paint smell as much. This stuff that evaporates because it's a liquid. You put it on the wall, there's liquid, and then as the liquid evaporates, you're left with pigment on the wall. The stuff that evaporates, all of that wasn't. There were some volatile organic compounds in that, and now there are fewer of them. Okay, particulate matter. Okay, excuse me. Oh, sorry. All right, carbon monoxide, sulfur oxides, nitrogen oxides, VOCs, particulate matter. Those are the primary pollutants that we put up. Where did they come from? Almost half of them come from transportation. Cars, trucks, buses, trains, planes, automobiles. Okay. 25% fuel combustion and stationary sources. What's that? That's power plants, that's furnaces, that's heaters, that's you're burning a fuel to heat your house. You're burning a fuel to run a power plant, right? You're burning a fuel somewhere else. Industrial processes, when you make some of the nice things we have, there's chemical byproducts. That's these. Solid waste disposal, miscellaneous. So this is where the primary pollutants come from, and then they can have chemical reactions and make secondary pollutants. Um, oh, primary pollutants, your VOCs, your carbon monoxide. One more, just another particulate matter. That's the stuff, soot, ash, dust. It's particles. It's not just a gas. It's a solid thing lifted up into the air. Secondary, you can make nitrous oxides can turn into nitric acid. You can make sulfur dioxide, can make sulfuric acid, right? The sulfur dioxide, you add oxygen, and then you get sulfur trioxide, and then you add water, and then you can get sulfuric acid out of it, all right? Um, Primary pollutants, there's the list. That's the list of secondary pollutants. Be good to the earth. We all breathe this air. Can't go somewhere else. Here we are. Be good. Okay. The atmosphere. We are so accustomed to the atmosphere, we ignore it all the time. All the time. You jump in a pool and you try and walk from one side to the other, and you feel the resistance and you feel the weighting, and it's an awkward motion. When you're walking across you don't swim through the air in front of you. One, it's not that thick, but two, you are so accustomed to it. You don't realize that the air is pushing all around you right now. You are at the bottom of a pool, swimming pool of air. And just like going deeper down into a swimming pool when the pressure increases and your ears pop near the bottom, we are at the bottom of this pool of air. So if we went up, the air is going to get thinner. The pressure is going to decrease. Here we go. Atmospheric pressure is right here in kilopascals. So Pascal is Newton per meter. So it's force per area. So it's concentration of force. So here it is at sea level, and it decreases just like this, like this, like this, like this, up to the top of Mount Everest, where it is a third of the pressure that it is at sea level. Now, this is not amount of air. This is not density. This is not the thickness of the air, but it's how hard the air is pushing on you. You keep going up, and the air gets thinner and thinner and thinner and thinner and thinner. In fact, there's a dotted line. You can make a line somewhere right about here. Half of all the air molecules in all that surround Earth are under that line. That's how thin it is up there for all that height. Let's see. So there you go. 50%. If you go to this height, you are above 50% of the air molecules. At this height, they did it in kilometers. Here we go. So at about 16 kilometers, you're above 90% of every air molecule. And at 30 kilometers, which is where this one cuts off, not the same scale, at 30 kilometers, you're above 99% of every air molecule. The atmosphere doesn't have this magic, like it's not air, 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 and then just space. There is no specific dividing line. It just gets thinner and thinner and thinner until nothing. There's gravity pulling down on the air molecules, and the air molecules are bouncing around hitting each other, and some of them leak out into space. Others, gravity pulls in. There is a difference in, right? Like there's no exact edge of space. The air just keeps getting thinner. But by this time, if you're above 99% of all the molecules, it's pretty thin out there. All right. Now, did I open that one? That one should be. There we go. I do have that chart open, so I don't need that page. Temperature. This is one of the things that might be the least expected. It gets cold when you go up a mountain. Temperature decreases. Yeah, absolutely. As you go through this level, temperature gets colder. Look, as you go through this level, temperature gets colder. Nope, wrong one. But as you go a little higher, temperature warms up. And then the temperature gets colder. And then the temperature warms up as you keep going up. I don't. There are reasons. They're real subtle, and we're going to go through a couple of them. But first of all, the layers. The layers of the atmosphere, troposphere. You live in the troposphere. The troposphere is actually not just about Earth. The troposphere is defined on every planet in the solar system. It's where weather happens. Weather happens in the troposphere. That's pretty much its definition. So there's clouds and wind and maybe rain or precipitation of some kind. That's the troposphere. And on Earth, as you go up through the troposphere, temperature decreases. In fact, these layers are the dividing lines. This is the troposphere, and then that dotted line is the tropopause, stratosphere and the stratopause. These dividing lines are based on where the temperature starts to go the other direction. By the way, this is in meters, so 10,000 meters, that's 10 kilometers. This is 30,000 feet. It's the height, so Everest is the same height like a 767 flies at. So airplanes fly right about the height of Everest. It's not a bad estimate. Man, sorry. Okay, troposphere. Then up into the stratosphere. That's next because that's not an airplane. That you kind of need crazy. You need fighter jets. You need oxygen mask. You need rocket. That's stratosphere stuff. Up into the stratosphere. Then temperature goes up in the stratosphere because that's where the ozone layer is at. The ozone layer is in the stratosphere, and the ozone layer absorbs all that UV light, that UV radiation. Well, when the oxygen ozone absorbs that radiation, it moves faster. And how fast it moves warms it up. And so the stratosphere is warming. As you go up, you get more and more and more UV light, more and more, faster. Now, notice that it does not get as warm as it was when you started down here at sea level. It's still colder, but it is getting warmer. Okay? So here it is, originally cold. All right, warm up, not quite to the same spot. Now the mesosphere. It's getting colder again. All right, temperature decreases. That's what's happening in the mesosphere. All right. That's it. In the mesosphere, it's getting colder. Then the thermosphere. Thermo sounds like heat and stuff. So it's going to warm up again as you go back up into the thermosphere. There is no upper boundary. There's no top limit. You just geese out into space. But the oxygen, O2, the nitrogen, they absorb radiation. Here's the thing. It is getting hotter as you go through this thermosphere. But the molecules are so thin, you wouldn't feel warmth on your skin if you had dared have exposed skin at that altitude, right? There's definitely no air for you to breathe. It's so thin, the idea of temperature even in space is kind of weird because temperature is actually measures how fast the molecules are vibrating. Okay. Well, when the molecules are thick, The faster they vibrate, the hotter it gets. That's what we experience. But up here, the molecules are so thin, they can't transfer any energy to you. So there's nothing coming in. It feels cold out there. But the one molecule, it goes flying by crazy fast. Well, since it's crazy fast, it has a high temperature. There's just not a lot of molecules to do anything. So that's kind of the definition of temperature that we use when you get to space. Space is super cold, right? Well, yes, it's cold because there's no molecules. But sometimes the single molecules you find are moving very fast, and each in one would have a high temperature. They're just cold, right? There's just not that many of them. All right. Now, Earth's atmosphere, big picture. Earth is tilted at 23.5 degrees. This is not a bad example of that. All right, 23.5 degrees, 90 degrees. Here we go. All right. So this is the light that comes in. So this, all right, you've got your Arctic Circle, your Antarctic Circle, right? Your Tropic of Cancer and Capricorn. I always forget which one's north and which one's south, right? So this is 23.5 degrees north. And when it's dead summer, the light comes in straight onto that. What this is saying is right here that light is at an angle, and it's not really shining at the North Pole. It's shining kind of almost across the North Pole, almost this way, right? So, what does all this do? Let's go up here. Yep. Here we go. All right. 23.5 degrees creates the seasons. We rotate on our axis and we revolve around the sun. Rotates day and night. Revolve is seasons. Actually, revolve is just year. Seasons are because we're tilted. 1, 2, 3, 4. All of these, the North Pole is pointed way up here, off screen is the North Star, right? It's way up here, past my hand, way up here. And so that's why it's always north. And if we're always looking that way and then we go around the sun like that, Northern Hemisphere is experiencing summer. Northern Hemisphere is experiencing winter because the light's at a greater angle. Then you've got spring and fall in between. So on the solstice, the summer solstice and the winter solstice, you have a very short day for the Northern Hemisphere and a very long day for the Northern Hemisphere. On the fall or the autumnal and the spring equinoxes, you have 12 hours of light for everybody. Okay? The seasons tilt. This is what's going on. All right. Just a reminder, solstices and equinoxes. Heat transfer. Okay. Heat and temperature. Temperature is the measurement of the molecule vibration. Temperature is the measurement of the molecule vibration. Temperature is what we're familiar with. Heat is not that. Heat is the energy that goes from one thing to the other. If I have a hot pan and I drop an ice cube in it, the heat, the energy from that pan that goes into the ice cubes and warms the cold molecules in the ice cube, that energy is heat. It's not temperature, it's heat. Heat is the movement of energy from a hot thing to a cold thing. And there are 3 ways. I know this has evaporation on here. We're going to forget that for a second. There are 3 ways to move heat as energy: conduction, convection, and radiation. Conduction is a simple one. It's got to be touching. This is a hot pan, and you grab the handle, and there's no pad on there, or the plastic's broken off, and you grab that metal handle. The heat from here is conducting and is touching you. You've got to have contact between 2 substances, the hot handle and you, or any 2 substances, and the energy flows from one to the other. That's conduction. Convection. Convection has to happen in a fluid. It's got to be liquid or gas. It has to be a fluid. Warm air rises, cold air sinks. Happens in a fluid here. The bottom of this pot's hot, so the bottom water gets hottest, and then it's going to rise up out of the way. When it moves out of the way, there's not some empty dry spot here. Cold water falls down in its place. And when you do that, you can get these cycles and these loops of convection currents moving, whether that's air or liquid water. Radiation's the third one. Radiation's a little different. Radiation is light. You can, from across the room, you can go up and put your hand near that burner and you can feel the heat coming off of that. That's not because it warmed the air and the air drifted over and touched your hand. Okay? It's because it's giving off energy as light. It's glowing. It's radiating. Right? If you see a chunk of metal that is glowing bright orange, you know that it's hot. That bright orange color is energy coming off of there. And some of that our eyes absorb, right? But some of that we feel as heat. It's a color our eyes don't see, but it's coming off of there. All right? Let's see what we've got. So conduction, convection, and radiation. 3 ways to move energy as heat. And if you need questions about radiation, we can look at that. But we're going to look at solar radiation. Solar radiation, last thing today. 500 watts per square meter averaged year-round on the Earth. What is that? 500 what? If I just drop 1 meter by 1 meter and put down a solar panel anywhere on Earth, on average, it doesn't have to be a solar panel, anything, it's going to collect 500 watts, 500 joules per second, every second average. Things near the equator, more. Things near the poles, less, except for the opposite seasons, right? So that's how much energy the sun's giving us. And remember, the sun's a huge sphere. It's giving off radiation in the opposite direction of Earth that we will never be able to get and collect and use. There's a lot of energy coming off the sun. But of what comes towards Earth, here's 100%. Half of it, whether it's direct and diffused radiation, is absorbed by land and sea. First of all, 5% is backscattered back into space. 20% is reflected off of the clouds. 20% is absorbed by the atmosphere, but then this 5% is reflected off the land sea surfaces. You add all that up, you get your 100%. Of all the energy that comes in, half of it is absorbed by land and sea. 20% is absorbed by clouds, right? Now, 20% is reflected from the clouds. 5% is reflected from land and sea. A lot of it is sent right back into space. There's a difference between reflection and scattering. Reflection is shining something, hits the mirror, it comes straight back. The beam in and the beam out, with sunlight in, sunlight out, are just as strong as one beam. Scattering, say you've got a water molecule or a dust molecule. The light beam comes in and hits that little molecule. When it does that, it doesn't bounce off as one beam. It hits it and it turns into 5 mini beams. Some of them go towards Earth and some of them go backwards. More of it's going to keep going forward than backwards. That's scattering. When you scatter light, it spreads out. And it's not one concentrated reflection. Let's look here and see what we get. 100% of solar radiation, right? 25% reflected off the clouds. Well, what did this say? This said 20% reflected from clouds. Okay, sure. 3% is reflected off the ground. What did this say? 5% is reflected off land, sea surfaces. So you got to be careful if you're talking about land or sea. Is it cloud or not? So you've got over here 33% direct, and then this other 10% down. That's how this one said direct and diffused. So it bounced off of something and then came down. All right, that's solar radiation coming to Earth, energy from the sun being used. All right, it was a good day. Remember, seniors, you're learning for good stuff, but this will not be on your test or on your final. Details online. Everybody have a great day.